Chapter 18, Maintenance, Inspection, and Troubleshooting. Now, let's start with the introduction. So, maintenance and troubleshooting are critical elements in ensuring the continued airworthiness, meaning the flyability of the aircraft, reliability, and safety of aircraft instruments and systems. This module introduces systematic troubleshooting philosophies, how to troubleshoot, modern diagnostic tools, inspection and replacement procedures, and the structured use of maintenance documentation in accordance with aviation regulatory standards. Basic troubleshooting philosophy. Okay, you have the systematic approach. Effective troubleshooting follows a logical, step-by-step process designed to isolate faults efficiently while minimizing unnecessary component replacement in order to precisely locate the fault, okay, and the fault source. The general philosophy includes verifying the reported fault, understand normal system operation so that we can differentiate between the fault and the normal operation of the system. Identify symptoms and affected subsystems. Isolate the fault through testing and analysis. Rectify the fault and verify correct operation. Okay, the troubleshooting efficiency can be expressed as eta is equal to n correct, which is the correct approach, divided by the total, like the number of correct fault identifications is n correct, divided by all or the total troubleshooting actions performed. That would give us the troubleshooting efficiency. You can say here, this is a metric that measures the difference or like the ratio between all the correct actions that had been taken in order to rectify the problem versus the total number of actions that some of which might not have been the correct measures to be, decided over in such scenario. In order to kind of memorize these steps that should be taken in order to troubleshoot, we can take the first letter of each sentence here and place them all together with one word. Okay, so that word would be VUIIR, which is verify the reported fault, understand normal system operation, identify symptoms, isolate the faults through testing and analysis, and rectify. Okay, so VUIIR, verify, understand the normal system operation, okay, then isolate the fault to check which are or what are the systems that have been affected through testing and analysis. Then, okay, so identify the symptoms, what is going on, then isolate, and finally rectify the fault or the problem. Fault isolation logic. Fault isolation commonly relies on decision trees and Boolean logic in order to identify a system fault. So let's say F is the system fault. A, B, C, and D represent contributing conditions such as power availability, signal integrity, sensor input, or control logic. So let's start with that. And we need to understand the Boolean logic so that we can understand when is a fault validated and identified as being a legitimate fault, not a glitch within the system. Now let's understand the Boolean logic so that we can learn when does the system check out as being failed, okay, or when does a system failure check out to be a true failure, not a system glitch, and based on what premises. So F is equal to A and B or C and D. What are A, B, C, and D? A is the power availability at the sensor. B is the signal integrity. So in other words, whether the signal is together or if it's like kind of cracked, can it be reliable and trustworthy? Can we read it and rely on its value. C, and C is actually the sensor input, okay, the input at the sensor. And finally, D is the control logic. So CTRL logic. Now, according to this formula over here, for F to be validated as a true system failure, either A and B should be true, or C and D should be true. So A and B should be true. Okay, to give you a picture here. A and B should be true, meaning that A should be 1 and B also should be 1. If either of them is 0, it would give 0, which is false. Okay, so if one of them or both of them is 0, the result would be 0. Okay, now for C and D, the same thing. Both of them need to be true, okay, for the result to give true. So C and D both should be 1 to give 1 as a like passed test, okay, as a result. If either of them is 0 or both of them is 0, it will all of these possibilities would give 0 at the input, which is a false test. Now, for the OR, what does OR mean? It means that either A and B should be true or C and B should be true. One of them, okay, should be true so as to check out as true. So if you have A and B here is 1, C and D is 1, or one of them is 1, the other is 0, in all these three cases, it would give you a true check, meaning that the engine would be, or the system failure would be considered and validated as a true failure, not as a defect within the checking system, okay, within the sensor, or like you have an interference at the data being collected from the sensor. This is the premise by which the computer would assess a system failure as a true failure, not as an error in reading the data from different sensors. Now, redundancy considerations. Modern aircraft systems employ redundancy to enhance reliability. Troubleshooting must consider the possibility of masked failures that are hidden. They are not necessarily reported on the screen. System availability is given by A equal MTBF divided by MTBF plus MTTR. MTBF means the mean time before, or I'm sorry, the mean time between failures, and MTTR is the mean time to repair. So the time between failures should be less than the mean time between failure plus the mean time to repair, so as to give the ability to the pilot to troubleshoot and maintain the problems of the aircraft. I'm talking about during the flight, okay, to troubleshoot and to fix the defects based on their capability in the air. This would be measured by this equation. In order to have an available system, this ratio should be as small as possible. Byte or built-in test equipment. Purpose and function. Built-in test equipment or byte provides automated fault detection and isolation within the aircraft systems. So automated detection of faults and also isolating these faults while recommending potential fixes, okay, or potential solutions for the problem. Okay, so the byte functions include post or power on self tests. Actually, it is pronounced power on self tests, okay, which means the self test of the computer system during the power on. Second, continuous background monitoring in the background of different systems. Fault code generation and storage for the diagnostics, later diagnostics on the ground. So the fault would be generated and stored for like later repair and reference, and for preemptive maintenance, and also maintenance data reporting. Byte architecture Byte systems typically consist of sensors and monitoring circuits, test signal generators, so generators that generate test signals in order to test the different faculties of the aircraft, non-volatile fault memory, which is a constant stable memory that would store permanently at times the faults that are being generated and that are being rather reported by the computer system, which are generated by the sensors. Okay, through the sensor readings, these faults are assessed as faults, and actually they would be packed as faults by the computers and generated by the computers rather. But the source is usually the readings from the sensors or the computers themselves. And these faults should be stored almost permanently within a memory on board. Okay, so you have non-volatile fault memory, and the detection probability may be modeled as probability of detection is equal to 1 minus exponential of minus lambda t, where lambda is the failure rate and t is the monitoring time. Okay, this is something like the law of Poisson, by the way, if I'm not mistaken. So the probability of detection is equal to 1 minus the exponential of minus lambda t, with lambda as the failure rate, and t is, or the frequency of failure, and t is the monitoring time. Limitation of byte. While byte improves maintenance efficiency, it may not detect, for example, intermittent faults, the faults that keep coming and going, okay, in an intermittent, like in a stuttering way, wiring degradation of the buses, for example, and environmental induced anomalies, like anomalies that are induced due to the environment, the ambient air, etc. False alarm rate is expressed as FAR, or false alarm rate, is equal to number of false reports divided by number of tests. Instrument inspection and replacement. Inspection intervals. Aircraft instruments are inspected according to flight hours. Also cycle count, which is each compression and decompression. Each time the aircraft flies and then lands, that would be one cycle. And calendar time. Inspection scheduling may be approximated by a function, okay, I being a function of HCT, where H is the flight hours, C are the number of cycles, and T is the calendar time. Calibration and accuracy. Instrument accuracy must remain within certified tolerances. Delta X is equal to X measured minus X true. Okay, so the allowable error limits ensure delta X, an absolute value, should be less than or equal to the maximum allowed number of errors, delta X max. So, in other words, delta X is the excursion or the difference or the gap between the measured value and the true value. This gap, this difference, should not exceed delta X max, which is the allowable error margin, so as to assess it or accept it as an allowed measurement premise, okay, an allowed measurement quantity on which we can rely to make a specific decision. LRUs, or line replaceable units. Most modern aircraft instruments are designed as LRUs to reduce downtime. Okay, so replacement procedures emphasize correct part number verification or correct model, ESD protection, which stands for electrostatic discharge, meaning that these instruments should be protected against any electrical discharge from a person's hand. Okay, this can be done by wearing the anti-static wrist strap, which is a strap around the wrist that is a good conductor for electricity. It would be connected to a ground bus so that while working with an instrument, any electrostatic charge within a person's hand would not go into the instrument, damaging it. Okay, it would be dissipating, and this charge within the ground bus, which is very important. Okay, protecting the instruments from any type of electrical surge that can actually damage the instrument itself. And post-installation functional tests, meaning after installation we need to recheck whether the instrument is working properly or not. So by conducting a test, we can verify that the instrument reinstallation or the maintenance had passed. Its check had passed correctly. Replacement effectiveness can be expressed as ELRU is given by, T saved divided by T traditional. So replacement effectiveness can be expressed as T saved divided by T traditional. This is the ELRU. By the way, T traditional is the classical maintenance time. Meanwhile, the T saved is the time saved by employing the LRU approach of replacement, which is replacing the unit itself, that is defected, not the entire instrument, so to speak. Maintenance documentation and manuals. Types of maintenance manuals. You have aircraft maintenance relies on structured documentation, including AMM or Aircraft Maintenance Manual, IPC or Illustrated Parts Catalog, FIM or Fault Isolation Manual, WDM Wiring Diagram, and MEL or Minimum Equipment List. Documentation hierarchy. Maintenance actions must follow approved data precedence. AD greater than AFM, greater than AMM, greater than company procedures. These are this is the sequence of priority for actions to be taken. First document to be to qualify as a guideline for maintenance, then AFM, then AMM, etc. Record keeping and traceability. Accurate maintenance records or accurate maintenance records ensure regulatory compliance and traceability, so that in case you had a misdiagnosis, a misrectification, and you can go back to the maintenance document so as to be able to assess what went wrong. The probability of undetected maintenance error decreases with documentation, so you can keep a complete tracking of the instruments and the entire situation or the entire condition of the aircraft. So probability of undetected maintenance error decreases with documentation completeness. The probability for error is proportional to the inverse of the quality detection. Safety and human factors in maintenance. Human factors play a significant role in maintenance errors. Risk increases with fatigue and workload. So the ratio of maintenance error is actually proportional to F times W, with F representing fatigue and W representing workload, or the total number of tasks that should be executed on an aircraft during maintenance. Final summary: maintenance and troubleshooting of aircraft instruments and systems require a disciplined, methodical approach supported by diagnostic tools, accurate inspections, and strict adherence to approved documentation. Effective maintenance practices directly contribute to aircraft safety, reliability, and operational efficiency.